We will continue with the lectures on control of time delay systems. In the last lecture, I showed you what a time delay system transfer function is. I explained physically why time delay occurs in terms of transport delay and so on, and derived a controller which basically takes this form right here, and that is where I stopped. And then I had said, for the first time we have a situation where the denominator is really not a polynomial in the transfer function model. So we have to think about how we are going to handle this, and as I said in the last class, since this is the first time we are seeing this, we have to identify what are the challenges that we might face, and what we need to do to solve those challenges. And basically the idea is, in most of what we try to do, once we find a solution for a type of problem, anytime we see some variations of that problem, we try to look at whether whatever solution strategy that we already have is applicable, and it might not be directly applicable. So we might do some approximation of our current situation, so that the solution that we have already seen could be readily applied. So we will try and see if we can do something like this in this case, to see if we could use whatever we have learned to solve the challenges that we face. So quickly, as a recap, the one thing I just wanted to point out again is that if I have a G model like this, then when I design a controller, you should be very familiar with this equation now, 1 by Gm, G desired by 1 minus G desired. And then if we were to take the G desired as a first order transfer function, which is what I want ideally, where tau c is as small as possible, so that whenever I give a set point, remember, just as a recap, y is G desired y set point if the model and the process are exactly the same. That is how we derived this equation for a controller. Now if this is a first order tau cs plus 1 with a very small time constant, then basically what it means is, whenever I have a step up, the output is going to follow the step very quickly without any offset, because the gain of this is 1. So that is the reason why we are always wanting the G desired to take this form. In fact, you could think of this as the simplest form, and the most ideal form we already discussed is 1, right? Y is y set point, but that basically means there is no dynamics associated with the response, which we have already seen is not possible. So we introduce a dynamics, but we want to introduce the dynamics so that the dynamics is not very overwhelming, right? So it's a very short dynamics, so this tau c has to be as small as possible. So that's the reason why we take desired like this. And another thing I would like to point out here is the gain of the G desired transfer function itself should be 1. So there is no point in taking G desired to be something like k tau s plus 1, where k is not 1. Then what you are basically saying is y is not going to be y set point, but some gain times y set point, which is something that we do not want. So in all the examples that we will keep choosing, you will notice that the gain of this G desired transfer function itself will be 1. Keep this equation in mind every time you think about G desired. This will kind of keep you on track in terms of understanding this. Okay, so from time delay systems, we have already seen this. I just wanted to recap this so that you understand again why we make this change here. So we said, if we simply substitute everything here, G model is, for example, tau s plus 1 by k e power minus tau ds. G desired is 1 over tau cs plus 1 divided by 1 minus G desired tau cs plus 1. Tau cs plus 1 and tau cs plus 1 will get cancelled. Tau cs plus 1 minus 1 will be tau cs. So this will lead to tau s plus 1 divided by k tau cs. And then this is what I am deriving, e power minus tau ds will become e power tau ds. Okay. Now it is very easy. So whenever you get this form, you notice that this is the PI form, and we will see this again and again. So if I simply expand this out, then this is basically, the first term is tau s by k tau is, so that will be tau by k tau c plus 1 by k tau cs. So this is typically the form that you keep getting. So now if you take this tau by k tau c out, the first term will be 1, and the second term I already have k tau z I have here, but I get an extra tau. To offset that, I will get tau s. Okay, now this you will see is the proportional gain, and this is the integral parameter in a PI controller. So, whenever you look at this form, you can always do this manipulation and then basically get it into the PI form that we have been using with the corresponding gain and an integral controller. Any case, so this is C. So, basically we know that U of s is Cs times E of s. So, the Cs has two portions. So, this is the PI portion. So, I am not even going into time domain, I am going to explain this in Laplace domain itself where the difficulty is. So, you can think of this C as having two portions. Typically, we will have only PI controller acting on the error, which is what we have been seeing all the time. But in this case, I have the Cs as a PI portion and an e power tau ds Es. Okay. So, that is what I need to compute to get my U of s. So, this without going into time domain, just in Laplace domain I can say this is EUS, a PI portion which is a controller, and e power tau ds E of s is going to be e power in time domain. When you convert this, what is going to happen is this is going to say somehow I have to get this E prime s, okay, and this E prime s which is going to be error t plus tau d, Laplace of that. Okay. So, if you think about this in the Laplace domain, so I can write this e power tau ds Es as some E prime s, and this E prime s is going to be a Laplace of this E of t plus tau d. Okay. So, if you now think about this, from the beginning we have been saying if you want to invert and then actually get an U of t, then you have to do a convolution integral between this Laplace function and this Laplace function, whatever the time equivalent variables that they represent. Then what will happen is you have to necessarily get values for E of t plus tau d. Okay. That basically means to make decisions about U of t, the input at time t, you need error at t plus tau d, which is not possible. That is the reason why we call it an unrealizable controller. So, this is an important idea to remember. So, we can think of this mostly in Laplace domain up to here, and here it is basically two functions. So, it is going to be a convolution of one by the other. So, this function is a PI function, this function will be basically E t plus tau d. So, that is an important thing to remember. I thought I will reiterate this so that you see why this becomes an unrealizable controller. So, that is the reason why if you want to get rid of this e power minus tau ds, going to the numerator and creating problems in terms of e power tau ds, making the controller unrealizable, we introduce this e power minus tau ds in the g desired transfer function itself. So, this is basically saying because there is time delay term in the model, I am going to simply say there will be some performance loss, and I am willing to accept that performance loss, otherwise I cannot even get a realizable controller. So, I am just going to say let me accept that, and the performance loss is e power minus tau ds. So, if you look at this g desired function, you will notice that the gain is 1 again, even though I have introduced e power minus tau ds, the gain is still 1. That means ultimately I will get to my y set point value. However, I will have a time delay. So, if there is a y set point change that is made here, y will do something like this. Ultimately, it will go there, but there will be a time delay here. Okay, and this is the performance loss I have. So, ideally, what I would like is something like this, but what I get is something like this. If tau c is small, I will get it as close as possible to this. But here again, this will just be shifted by tau d, which is basically something you do not want, but there is no way around it. So, you basically say let me lose that performance. So, the consequence of that choice is that when you actually compute these Cs, you get g desired by gm times 1 minus g desired. When I plug in all of this, now you notice that I have Cs is this. So, if I do Us is Cs times Es. Now, here I had this e power tau ds and a pi. Now, I do not have that. So, I have some other form which does not look like a pi, but this is some other form, but that is basically going to act on only error at time t. Okay. So, at least the unrealizable problem we have gotten rid of. However, we have a new problem because we have a controller transfer function which is in a form that we have not looked at before, and we do not know how to handle this at this time. So, we have to figure out what are the ways in which I can handle this transfer function. So, I hope till now it is clear in terms of why we have to introduce this time delay in the desired and why that creates this new headache for us, which is that the CS is not in the numerator by denominator form, which we are very comfortable looking at, and for which we have all kinds of tools in terms of how to implement these, how to invert these and so on. Okay. So, you will have to see how we are going to do this. So, again I have just written the same thing here. I have an input which should be a function of the controller times the error, and that basically gives me this equation. Typically what I have been doing is I have said this is a numerator by denominator polynomial. Usually we can do Laplace transform and the convolution to kind of identify what u should be. So, those are things that we have been talking about. However, now I have this in the denominator which is not a polynomial. The problem is the tool that I have taught you till now is partial fraction expansion, but this is not possible here because I have an e power minus tau ds, and I am going to kind of talk about this in a slightly simple perspective. I am not going to go into all very exact mathematical details, but just to give you a feel for why the problem comes and how we can think about addressing this. I am going to kind of put this back into the partial fraction framework and then ask the question, if I know how to do this, if I have a numerator by denominator polynomial. So, is there some way in which I can convert this to a polynomial so that I can continue to use the techniques and tools that I have in my bag. Okay. So, one way to do this would be to kind of expand this as a polynomial, and we all know that when we expand e power x, you will get a polynomial of finite order. You keep adding more and more terms, and if you conceptually think about this without worrying about all the mathematical details, you will notice that I am going to get a denominator polynomial which is going to have infinite roots. So, basically there are going to be infinite terms in the partial fraction. So, which is going to be a problem. Okay. So, that is problem number 1 when I have this time delay term. Of course, consequently the other problem is, if I want to look at the stability of the systems, it looks like a even bigger headache, because if I think of a large number of poles through a polynomial expansion, then I have to ensure that all of these poles are in the left half plane, right. So, if even a few of these move on to the right half plane, or even if one of these move on to the right half plane, then I have a problem. So, one has to ensure that the large number of poles, none of them are in RHP. So, basically the sequence in which we have done this, right, all of this computations we have done using partial fraction, that is not possible anymore, is the first thing that I want to explain. And number 2 is that if it is simple partial fraction, then we know how to do stability, right. So, we get it in the root resolve form and we look at all the roots. If all of them are in LHP, we say the system is stable. However, because partial fractions is not possible, we cannot do that for stability. And of course, even when partial fraction ideas were not directly possible, we had used Ruth table to think about stability, and if you want to see whether we can actually use Ruth table here, that is also not possible, because for a Ruth table, even if the denominator is not done in the root resolve form, we can only work with finite polynomials, whereas here, because we can keep expanding e power minus tau ds, the polynomial terms are also not finite. So, doing Ruth table is also not possible. So, the question is, how do I invert this so that I get my partial fraction ideas working, or I have to find some other way of thinking about it. And of course, once I figure that out, then I have to really worry about the stability of the systems. How do I address the stability of the systems when both the notions from partial fractions that we have talked about and root stability, both are root table, both do not work anymore. So, one standard technique that we could adopt is to say, look, I am going to use the Taylor series expansion, and I am going to use only a few terms and then see how good the approximation is, and then proceed with doing everything that I have been doing till now. Now, notice this, if I do this polynomial expansion, then actually I can put this in the numerator by denominator polynomial form, then all the techniques that we have learned come back into play. I can use any of those techniques and then I do not need to do anything more. So, conceptually, if I were to live with using this polynomial expansion up to a certain number of terms, I do not need any other new idea to do this. I can simply follow what I have been doing. So, typical expansion for e power minus tau ds would be 1 minus tau ds plus tau ds whole squared by 2 factorial minus this cube by 3 factorial and so on. So, you can keep going. Now, if you say, okay, I am going to use only the linear term. So, if you take this, then you could put this here and then put this e power minus tau ds back into your controller equation, then everything is done, right, because I can again use the numerator by denominator polynomial idea and do the inversion and then easily live with whatever we have learned. However, this form, so we are going to do that, and I am going to teach that as one technique for dealing with the time delay systems, but I am going to tell you that when you deal with time delay systems in that format, it is going to be somewhat approximate. This is of course grossly approximate, very inadequate, but there are smarter and better ways of doing it, and still you can live with analyzing time delay systems using the standard polynomial based ideas that we have seen till now. Okay. So, if this is grossly inadequate, is there something that better I can do? So, better approximation for this is what is called Pardes approximation, which basically what it does is it takes e power minus tau ds and then it kind of splits it into 2, right. And the reason why you want to do it is that you are kind of balancing the poles and zeros that you get in this expansion. If you look at this e power minus tau ds, you keep increasing the poles, but nothing happens as far as the zeros are concerned. However, here there is some balance between poles and zeros, and this is a much better fractional approximation than this kind of approximation that you might have. Notice that in this case e power minus tau ds, you are approximating it as a system with 1 0 and 1 pole. In this case, you are approximating it as a system with 2 zeros and 2 poles and so on. Now, we do this, then basically if you notice in the previous slide, I have this tau cs plus 1 e power minus tau ds and I have tau s plus 1. So, if I have this equation here, now if I just do this tau s plus 1 by k tau cs plus 1 minus some numerator polynomial by denominator polynomial, depending on whatever order Pardes approximation I am going to use, then I can multiply this by the denominator polynomial, take it to the top and then simplify it. I will get some numerator by denominator polynomial form. Okay. So, once I get my numerator by denominator polynomial form, then the basic ideas are the same. You can simply look at how to do the expansion of this and work with all of these other things that we have taught you. Okay, so a simple example, let us say if I have transfer function of the form 4 e power minus 3s divided by 1 plus 2s, then if you write your e power minus 3s as a Pardes approximation, it will be 1 minus tau ds by 2, so it will be 1 minus 1.5s divided by 1 plus 1.5s, then you can put this into this transfer function and then you will basically get a transfer function. Now that you have this transfer function, basically you can use all the techniques that we have talked to you about, which is doing the numerator by denominator polynomial. You can think about getting your controller and stability. All of those are things that you can start looking at. So, basically for time delay systems, one way of designing the controller is to use Pardes approximation for your process and then simply go ahead and do the standard techniques that we have been looking at. So, if I have a g of s, you could with a time delay function, then you can get an approximate g of s, which will be in the numerator by denominator form, because I am going to convert this e power minus tau ds into a Pardes approximation, which has a numerator by denominator. And once you have this numerator by denominator form, you choose the corresponding G desired that will make the overall controller one of the forms that you are comfortable with, the PID form, and then go through the same direct synthesis procedure, you will get a controller. Now, an interesting thing to notice is this is G of S even in the model. So, this actually whatever we have is really a G model of S, because I want to keep distinguishing between the model and the process more and more as we go through this course. So, even the model itself, we are making it even more approximate using this Pardes approximation, and then we do a G desired, and then we can get a controller. Okay. So, once you have that controller, then if you want to analyze it for a true process, then you have to actually say in the control loop, I have a controller which is derived based on a model for which I got an approximation based on Pardes approximation, and then actually the GP could even be slightly different from the original model that you took. Okay. So, it could be 4 times e power minus 2.5 s. So, you kind of wrongly estimated the delay, let us say. Then you can actually kind of do the analysis where if you say my process is slightly different from the model that I have used, how would my controller still perform is an analysis that you can easily do now by choosing different G process that could happen. So, that way you can actually study the robustness of your controller for time delay when the time delay that you have actually have in the process is slightly different from whatever was used in the model and so on. But the key idea that I want to leave you with is this G model itself is an approximation of this process, and we do a further approximation using Pardes approximation, and once we do that, then the controller design is standard, because I will get the numerator by denominator form. I can actually look at how to do the design using my standard direct synthesis approach. So, this is one way of doing this. I might also ask if there are better ways of doing this without doing this Pardes approximation, and if there are better ways of doing this without doing the Pardes approximation, how do I do it? How do I realize the controller? And more importantly, once the controller is realized, how do I understand the stability of the controller? Can I go away from the numerator denominator polynomial form and the ideas associated with it, and then bring in some other newer ideas that can be used for analyzing these systems and understanding control of time delay systems. So, this is what I am going to teach you in the next lecture. Thank you.